Hey, it's me, Nelson, here again to talk to you about circuit stuff. Hooray! This time I'm going to talk to you about nodal analysis. Now that you guys are masters of all the laws you need, you can examine most circuits and use nodal analysis to solve them. That's what I'm going to teach you how to do. It's not that hard. It's fairly systematic. One of the main reasons we use it is because it's so systematic, and we can program into computers really easily. Anyways, it's also really easy to learn, but the easiest way to learn it, of course, is through example. So let's get started on a very simple example right now. Whoa, look at this circuit. Look how fancy it is. So, the very first thing you want to do with nodal analysis, as you might suspect, is identify the nodes. And as I previously mentioned, a node is any section of the circuit that is connected to three or more branches. Branches being fairly self-explanatory, I would hope. Um, so, in the case of this circuit, there are exactly two nodes. One right there, and this entire bottom rail is also one node. Now, these two little corner guys right here, they're not nodes. What they're called is binary nodes, and what that means is that they're connected to there's a branch on either side, so it's like it's part of the same branch. And although you can do nodal analysis using binary nodes, it just adds more variables that you don't need and it makes it more complicated. So we generally just sort of ignore them. Now, after you've identified all the nodes in a circuit, also just as a quick sort of note, pretty much the minimum amount of nodes you can have is two, including binary nodes. You could have like two binary nodes, but if you only have one node, then what that means is either a load hooked into itself, which is pointless because a load can't do anything to itself, a source hooked into itself, which is dangerous because you generally don't want to short circuit a source, or it's a wire. Wow, you wire. That's really interesting. So generally, two nodes is going to be the minimum. And one thing we have to do with the two nodes we have is that we have to select one as ground. Because what we're doing is we're going to find the voltages of all the nodes. But a voltage is a relative measurement. You can't just say like that thing has 7 volts. It's not like mass, which is, absolute. So we need to select one node to have 0. Now generally, you can choose whatever node you want. You choose it as it's convenient. In this case, it doesn't really matter which one we choose. But let's say we had one that, like there's a whole bunch of nodes and each node was hooked up to one other node, except for there was one node, like right in the middle, that was hooked up to like 8 different nodes. You'd probably make that one ground because that would result in the most number of zeros in all your equations. In this case, just because it looks nicer, I'm going to draw ground on the bottom. This is the symbol for ground, or rather it's a symbol for ground. There's lots of symbols for ground. You could also, if you would like, put a triangle, or what I see fairly often is like this. I don't draw this one very often because I'm not very good at art, and it always looks really silly and kind of looks like a broom to me. So I usually do the 3 lines. So now that we have all our nodes, and we have selected one node as the reference node, we then have to write equations for every other node. Now, which equation do we use, you may wonder? We use KCL. That's right, Kirchhoff's current law, the very useful thing I talked about last time. We use it for every single node. Now, luckily, this only has one node, so we only have to write one KCL equation, and that's pretty easy. So let's just label this here. So with nodal analysis, we assume all currents are exiting the node. You could assume all currents are entering the node also. The only difference is negatives. If you choose all currents exiting the node, most things are positive, and if you choose all currents entering a node, then most things are negative, and so we generally choose exiting a node because it's a little bit less confusing. So let's call this one I1, this one I2, and this guy right here I3. That's a 3, by the way. You can't tell, but that's what it is. So what's the KCL expression for this node? Well, if you remember, it's the sum of all currents is equal to 0. I'm not sure why I drew the sum symbol. So basically, for V, and let's just call this one V1, because it's the first node. That would be I1 plus I2 plus I3 is equal to 0. So that's a pretty simple equation. Too bad we don't know what those are. And that's really where nodal analysis comes in, is that you then find what all those currents are equal to. So let's start with I1, because it's by far the simplest. This guy right here, in case you've never seen one of those before, is a current source. And what a current source does is it sets the current in a branch to something specific. In this case, 3 amps. That means we know for a fact that there's a current of 3 amps going this way. So we already know what I1 is. How fancy-dancy for us. I1 is equal to 3 amps, but it's not actually equal to 3 amps because, as you can see, this is going into the node, but we want current exiting the node, so it's actually negative 3 amps. Pretty simple. You may have noticed that I have a resistor there that's not labeled, and you may be like, well, how am I supposed to solve a circuit if I don't know all the resistances? What are you talking about? And the reason I put that there is to show you that this resistor, this guy right here, doesn't matter. We don't care what that is. It could be 2, it could be 2,000. It actually wouldn't affect the voltages at all. It affects what the voltage drop across that specific resistor is, and it will also change the voltage drop across, the current source. But as far as finding the node voltages, it doesn't matter. So we can pretty much ignore it. Hooray! Now, I2 is a little bit more complicated, but still not so bad. If you remember, the current across any conductor, or through any conductor, I should say, is equal to the voltage across that conductor over the resistance of that conductor. So all we have to do is find the voltage across a branch and the total resistance of that branch. If we put, the start voltage here and the end voltage there. So generally, what we would say is that it's equal to the voltage of the first node minus the voltage of the second node over the resistance of the branch. And that's a general statement for all nodes with just a resistive load between them. But in this case, how fancy are we? We already know the voltage of the second node. It's 0. We made it 0 because of the ground. So we can actually just replace this guy with a 0. How cool is that? And of course, the resistance is equal to 4, because there's 4 ohms in there. Isn't that lovely? That's not so bad, right? So now we know I2, it's just V1 over 4. So finally, all we have to do is find I3. Now, I3 also not that complicated. Slightly more complicated because of the the voltage source, but really not that bad. What we can do, instead of using, can I get rid of that? There it is. You may be like, well, how do we deal with this voltage source? And so I'm going to show you an equation, and I'm going to give you a reasonable way to think about why it works. So if we know that the current through one branch always has to be equal, that means if we put the two endpoints right here, we should get the same current is if we put the two endpoints there. Now, what's this voltage, you may wonder? Well, that voltage is the voltage of the reference node plus 12. So all we have to do is go V1 minus the voltage of the reference node plus 12 over the resistance, may as well just write it down right away, over the resistance of the branch 6. So that's I3. Let's just write that down. This is equal to plus V1 minus 12 over 6. And that's equal to 0. So there you go. The full equation, the full KCL equation for every single non-reference node in this circuit. Now, you can go about solving this however you feel. It doesn't actually matter which way you do it. But I'm going to show you the way that is sort of easier to follow when we move on to circuits with more than one non-reference node. In that case, we'll need systems of equations. So all we can do is move this minus 3 over. We're going to want to keep all the expressions with variables on the left and all the expressions without variables on the right. So we have a quarter plus a sixth multiplied by V1. And that is equal to 3, moving the 3 over. And then if we move the negative 12 over 6 over, we get plus 2. So a quarter plus a sixth of V1 is equal to 5. And if we solve that equation, what we should get is that, now, did I actually write it down anywhere? I didn't, so just give me 1 second. Sorry about this. 5, 4 over, 6 over, add those two together, and then it's 5 divided, should be equal to 12 volts. Curious. That's just a coincidence. It has nothing to do with the fact that that source there is 12 volts. For example, I believe if we get rid of this, oh my, if we get rid of that, just give me a second here. I think I can get this to work. Oh, okay. This program's a little bit weird. If we change this to 8 volts, or 8 ohms, sorry, then what we will get instead of, I believe we get 17.1. So what that would mean is we get rid of this quarter. And this is a learning experience because, you can see how it affects it. Oh, wow. This is me screwing up. Sorry. So if we go an eighth plus a sixth, you can't see me obviously, but I'm doing this on a calculator. And then we do that under 5. Yeah, 17.14. So let's just write that down. 17.1. Roughly 17.1 volts. And there you have it. So, pretty simple, I hope you feel. Now it's time, now that you guys are masters of the single node circuit, it's time to move on to something a little bit more complicated. Just a little bit more complicated. Don't worry about it. It's just going to be basically the same circuit, but with 2 non-reference nodes. Count them up. 2. 1, 2. So I need you to calm down. I need you to take a step back, take a breath, and realize that you are perfectly capable of doing this with everything I've already taught you. But in case you're just not confident enough in your own abilities, I'm going to go through it right now. And just because we should probably be specific, let's call this guy V1 and this guy V2. So let's do V2 first because it's a little bit simpler, a little bit easier. The only reason it's easier is because you may have noticed I reversed the direction of this voltage source. Not that big a deal. You'll see all it really changes is a negative to a positive. But I figure, hey, may as well leave that till last. So, V2, we have the current source, -3, plus V2 over 4. That's this branch right there. And the other branch, so remember, it's the voltage of the first node minus the voltage of the second node over the resistance. So in this case, it'd be V2 minus V1 over 20. Perfect, and that's equal to 0. Ta-da! That's already one of the equations done. Not even that big a deal. Now V1, very similar. We'll have V1 over 8 plus. Now in this case, remember that we're assuming that all currents are exiting the nodes for both nodes. So when we were doing the V2 equation, we thought the current was going this way. But now that we're doing V1, we're assuming the current is going this way. Doesn't actually matter. It'll figure itself out. So in this case, we go V1 minus V2 over 20. And then for the branch with the current source, it's pretty much the same thing. You just have to remember that now this part of the branch isn't 12 volts higher than 0, it's 12 volts lower. So it's V1 minus 12. So that's going to be plus 12 over 6. And that's equal to 0. See, I told you it was just a minus sign. And so, now those are your two equations, and you can go about solving those however you want. I'm sure you guys are very good at solving algebraic equations. But for the sake of a future video, when I show you guys how to do this by inspection, I'm going to show you how to do this with matrices. Because matrices are actually super useful and actually pretty nice. You might not think that solving two equations of two variables is really that bad, but if you get a more complicated circuit that has 100 equations and 100 variables, 100 by 100 matrices aren't that nice, but they are a lot nicer than having to plug equations into each other 100 times in a row. Also, it's easier to find a computer that can do matrix calculations than it is to find a computer that can solve systems of equations for you. So, I'll show you the transition step, I guess. So for V1, we have an 1/8 plus a 20th plus a 1/6 of V1 plus, and remember, keeping all the variables on one side, negative 1/20th of V2, and that's equal to, now this time we're moving the positive 12 over 6 over, so it's going to be equal to -2. And then for V2, very similar equation, we're going to have negative 120 V1s plus 1/20th, plus 1/4 of V2. And that's going to be equal to 3. And so the reason I wrote it like this is because this is easy to put into matrix form. So, for you guys who remember your matrix calculations, if we have a matrix A times a vector X, and that's equal to some other vector b, then we know that the vector x is equal to the inverse matrix of A multiplied by the vector b. So all we have to do is figure out which vectors we need and which matrix we should use. So our unknowns are not, x, y. It's not anything Cartesian. What it is the voltages. So let me just draw the matrices here. It's going to be a 2 by 2 matrix because we have two equations. And then that's multiplied by 2 by 1 vector. And that's going to be equal to some other vector. So we know that we want our unknown vector to be the vector of voltages. So let's put in V1 and V2. Sorry, not times anything. So what do we put in the matrix? Well, we just go spot by spot. So in the top left corner of the matrix will be how many V1s we have in the V1 equation. So in this case, it'll be 1/8 plus a 20th plus a 1/6. And then the top right will be how many V2s we have in the first node equation. And that's negative 1/20th. And so for the bottom row, it's going to be using the second node equation, in which case we have negative 1/20th V1 and 1/20th plus a quarter V2. So now what do we have? What are we going to put in our vector B? Well, let's see. For the top spot here, what we want is we want something that's equal to 1/8 plus 1/20th plus 1/6 V1 minus 1/20th V2. Now, if only there was some equation that would tell us exactly what that's equal to. Yeah, that's right. You guessed it. You put a -2 in there. And similarly, you put 3 in here. Now, all you have to do is invert this matrix and multiply it up. You're probably not going to be doing that by hand, I imagine. You're probably going to get a calculator to do it or some sort of computer system to do it for you. If you're doing this in real life, you'll almost certainly have a calculator with you. I can't imagine you're ever going to need to do nodal analysis on a beach somewhere, without a calculator. I don't know what you get into, though. I have no idea what might come up in your life. I pray that you never get into that situation. And so if you invert this matrix and multiply the inverse of the matrix by the vector B, you'll find that V1 is equal to... Yeah, I did write this one down. I'm not that much of an idiot. Negative 4.5 volts. And V2 is equal to positive 9.25 volts. And there you have it. It's as simple as that. Now, I know this is maybe a lot of information to sort of take in all at once, but it's really not that complicated. I'm sure you can find lots of examples online if you're really interested. It's pretty straightforward. The only thing that's really hard is maybe the matrix thing, and you can ignore that if you just prefer to plug equations into each other. Anyways, now that you guys are masters of multiple node circuits, and you guys are really progressing fast, holy crap. I don't know if I can compete with this sort of... I think I have to stop teaching you, because you're sort of encroaching on my territory at this point. Come back next time, and I'll tell you how you can skip... let me see here, where's my mouse? You see all this that we did? All this, and everything? Yeah. You can ignore all that. You can skip all that. It's called Nodal Analysis by Inspection, and I'll teach you how to do that next time. Anyways, bye.